There has been an announcement from NASA, and let me read this.
To arrange things into the patterns that we see, there's something else there. There's something beyond the galaxies that we see, the visible matter.
In 1977, NASA launched two small probes called Voyager One and Two on a routine mission to study the outer planets. Decades later, those same spacecraft reached a place no mission was ever designed to study, the edge of the Sun's domain.
Right now, the two Voyager spacecrafts are hurtling through interstellar space at 35,000 miles an hour.
It's actually speeding up in its expansion.
What they reported stunned scientists. A sharp boundary in a region so extreme it was described as a blistering wall tens of thousands of degrees hot.
I couldn't believe how nature was fooling us.
It wasn't supposed to be there, and no one fully agrees on what it really is.
And because Voyager was not designed for that, miracle fit that all this team is able to pull out the signal and tell us what's going on.
The Wall of Fire. When Voyager 1 launched decades ago, the mission was very clear. Each spacecraft carried cameras, scientific instruments, and a golden record filled with pictures and sounds meant to represent life on Earth to communicate who we are, if the spacecraft are ever found, by offering a snapshot of life on Earth to any intelligent beings that might encounter them. No one imagined the spacecraft would still be working more than 40 years later, long after they had passed the planets they were originally sent to study. Their journey was made possible by a rare alignment of the outer planets, an event that happens only once every 176 years. This special lineup allowed the spacecraft to use each planet's gravity like a push, swinging them forward toward the next planet while saving fuel and time. Voyager 1 flew past Jupiter and Saturn, sending back stunning images that completely changed how people saw those massive worlds. It revealed huge storms on Jupiter larger than Earth and showed Saturn's rings glowing like ice in the darkness of space. Voyager 2 took a longer path, traveling farther and becoming the only spacecraft to ever visit Uranus and Neptune up close. After finishing their planned missions, both spacecraft faced an unexpected future. Instead of shutting down, NASA made the decision to let them keep going. The Voyagers were allowed to drift farther into space, heading toward a region no human-made object had ever explored before, the great unknown beyond the planets. Now, beyond the planets we know, at the edge of our solar system, space starts to behave differently. It grows quieter, stranger, and full of mystery. This is where NASA's Voyager 1 spacecraft has been traveling for decades. It's the most distant human-made object ever, sending back faint signals from the boundary between our Sun's influence and interstellar space. In this distant region, scientists discovered what they describe as an invisible wall filled with extremely energetic particles. If you could be there, those particles would register temperatures around 89,000, 540,000 degrees Fahrenheit, far hotter than the Sun's surface. Yet Voyager doesn't burn up because space is nearly empty and there aren't enough particles to transfer heat. This boundary is called the Heliopause. It marks the outer edge of a huge bubble around our solar system, created by the solar wind, a constant stream of charged particles flowing outward from the Sun. That wind acts like a shield, protecting the planets from much of the radiation coming from the galaxy. Eventually, the solar wind runs into the thin material between the stars. Where the Sun's outward push meets the pressure of interstellar space, the heliopause forms, the true edge of the Sun's reach. Voyager 1 crossed this boundary in 2012, revealing that the edge of our solar system isn't calm or empty, but an active, energetic frontier. Why the temperature jump? All of this naturally raises a big question. If space out there is so empty, so cold, and so far from the Sun, how does a place like this end up being so hot in the first place? To answer that, we have to rethink what temperature really means beyond Earth. The dramatic numbers Voyager records aren't about heat you could feel, but about energy, the speed and violence of tiny particles moving through an almost perfect vacuum. Once you understand that difference, the sudden temperature jump at the solar system's edge starts to make sense, and the invisible physics shaping this strange boundary come into focus. Machines like Voyager measure this energy by detecting charged particles and plasma waves to infer temperature from their motion. That's why Voyager can record readings like 50,000 Kelvin without literally burning up, because space is so empty that those particles rarely collide with the spacecraft itself. So where do these energized particles come from? The Sun is always releasing tiny charged particles, mostly electrons and protons, that shoot outward through space at very high speeds. Near the Sun, this stream spreads out easily, moving freely before it begins to slow down or interact with anything around it. But as it travels farther out, it eventually encounters resistance like a strong headwind. At a certain point, the solar wind slows abruptly, creating a region called the termination shock, a kind of cosmic traffic jam where the particles lose a lot of their forward motion and are compressed and heated in the process. Beyond that is the heliosheath, a turbulent layer where the solar wind is slowed, mixed, and diverted as it presses outward toward the edge of the Sun's influence. The very edge of this bubble is where all the action happens. Two winds blowing against each other, one from our Sun and one from the galaxy itself. At the heliopause, they meet and push back with roughly equal force. This collision doesn't just slow particles down. It creates what scientists call shock waves and compression zones. When flows like these crash together, the energy from their motion gets scrambled into other forms, especially kinetic energy, which shows up as superfast particles. That's why the region around the heliopause shows such high temperatures, even though the actual density of particles is extraordinarily low. You can think of shock waves in space a bit like the shock a jet creates as it flies faster than sound, or like the ripples that form in front of a fast-moving boat. Those disturbances are places where energy gets concentrated, and in space that energy ends up going into particle motion. Particles get bounced around, scattered, and sometimes reflected between magnetic fields and waves, and each bounce can accelerate them to even greater speeds. This process is part of what scientists call particle acceleration. The magnetic fields carried by the solar wind and by the interstellar medium also get compressed and tangled at the boundary, adding to the chaotic energy environment. Another piece of the puzzle is that some particles from outside the solar system, cosmic rays, are pounding in from all directions. When these very high-energy particles interact with the slower, denser solar wind at the heliopause, they contribute to this energetic mix. Voyager's instruments have seen lots of changes in particle types and speeds as it crossed this boundary, confirming that it's not a smooth fadeaway but a dynamic collision zone where energies spike, particles are reflected, and complicated plasma physics takes over. What this means for space science. What Voyager uncovered here forces scientists to rethink how our solar system fits into the larger Milky Way, how effective our cosmic shield really is, and what the true nature of interstellar space looks like. That's where the discovery moves from being fascinating to being transformative.
We thought we'd see bands and other colorful things like we had seen at Jupiter and Saturn, and Uranus presented to us a blank face.
For decades, researchers imagined the heliosphere as something fairly smooth and predictable, gradually thinning out until it quietly faded into interstellar space. Voyager's data shattered that idea. Instead of a neat boundary, the spacecraft revealed a complex, active, and sometimes chaotic region where particles, magnetic fields, and energy behave in ways older models didn't fully predict. This forced scientists to go back to the drawing board and rethink how the Sun's influence suddenly stops. One of the biggest surprises was how sharp and dynamic the heliopause turned out to be. Classical models suggested a more gradual transition, but Voyager showed that the change in particle behavior and magnetic conditions happens over a relatively narrow region. As Voyager 1 crossed the heliopause in 2012, it detected a sudden drop in solar wind particles and a sharp rise in cosmic rays from outside the solar system. Even more striking, the magnetic field direction didn't change as dramatically as expected, meaning the Sun's magnetic field and the galaxy's magnetic field may be more connected or aligned than scientists had assumed. That single observation challenged long-standing assumptions about how magnetic boundaries in space should behave. This means that the heliosphere isn't just a scientific curiosity. It acts like a protective shield. The bubble deflects and weakens a large portion of high-energy cosmic radiation that constantly travels through the Milky Way. By learning how the heliosphere interacts with the interstellar environment, scientists can better understand how much radiation reaches Earth and other planets, and how that exposure may have changed over time. Voyager's measurements also help researchers model how cosmic rays slip through gaps or weak points in the heliosphere, which has implications for everything from astronaut safety to the long-term habitability of planets. Voyager has also given scientists their first direct taste of what interstellar space is actually like. Before these missions, everything we knew about the interstellar medium, the thin gas, dust, and magnetic fields between stars, came from telescopes and indirect measurements. Voyager is sampling it firsthand. Its instruments have measured the density, pressure, and particle makeup of this environment.
And it also had a very thin atmosphere. And the atmosphere had these cloud structures in it, these very, very thin, narrow clouds.
Showing that interstellar space is not empty and quiet, but filled with moving plasma and magnetic turbulence. There are also very practical benefits to this knowledge as well. Future missions may one day be designed to travel far beyond the planets, possibly even into interstellar space on purpose rather than by accident. Knowing what kinds of particle radiation, magnetic disturbances, and shock regions exist at the Heliopause helps engineers design spacecraft that can survive the journey. Voyager's experience serves as a real-world stress test, showing which instruments last, which systems degrade, and how electronics behave in an environment no human-made object had ever entered before. However, the most important note that scientists have made so far is that Voyager's discoveries remind scientists that our solar system doesn't exist in isolation. It's embedded in a living, moving galaxy, constantly interacting with forces far larger than the Sun itself. What's next for Voyager? Right now, both Voyager 1 and Voyager 2 are still out there, way beyond the planets and past the Heliopause, the boundary where the Sun's influence fades and true interstellar space begins. They are the most distant human-made objects ever sent into space, and every day they still send back tiny bits of information from a place no spacecraft has ever studied up close. But the Voyagers are old, launched in 1977. They were originally only supposed to last about 5 years. They're still operating thanks to their radioisotope thermoelectric generators, which produce electricity from the heat of decaying plutonium. However, the bad news is those generators slowly lose power, about 4 watts per year, because the radioactive material decays over time. That means mission engineers have to make tough choices about what systems stay on and what gets turned off so that the spacecraft can keep functioning as long as possible. Because of the shrinking power supply, NASA has been gradually shutting down instruments that aren't essential for the Voyager's current mission, studying the space outside the heliosphere. A few years ago, cameras and instruments meant for flying past planets were switched off long ago, and more recently, Voyager 1's cosmic ray detector was turned off to save energy, with other instruments on both Voyagers being paused in a planned sequence to stretch each probe's life. Right now, each spacecraft has 3 science instruments still running, and those are carefully chosen because they tell us the most about the local interstellar environment. They measure things like magnetic fields, plasma waves, and sometimes charged particles, all of which help scientists understand the invisible forces and materials in the space between stars. For example, the magnetometer tells us how magnetic fields behave out there way beyond the Sun's bubble, and plasma wave data can reveal how interstellar plasma is structured even thousands of times farther from Earth than Pluto. Voyagers also help scientists track cosmic rays, which are high-energy particles that zip through space. These particles are more abundant beyond the heliosphere than near Earth, and by watching how their intensity changes, Researchers can see how effectively our solar bubble shields us from this kind of radiation. Even with the clever power-saving strategy of turning off less essential systems, the Voyagers won't last forever. As the RTGs continue to fade, engineers expect that the spacecraft will gradually have to power down instruments, one by one, until only one remains, and eventually even that won't be sustainable. Right now, experts suggest each Voyager could keep at least one science instrument running into the early to mid-2030s, provided nothing unexpected goes wrong. After that, they may still be able to send back simple engineering data, like whether a transmitter or thermometer is still alive. When the last instrument finally goes silent, the probes won't stop drifting. They'll continue coasting through the galaxy for tens of thousands of years, eventually heading toward the distant Oort cloud and beyond. But by then, Voyager won't be sending data home, and all we'll have left are the incredible discoveries they already made from the edge of the solar system and into interstellar space. What has Voyager done for us? And this is where Voyager's story takes on a different kind of weight. As the spacecraft slowly runs out of power and its instruments fall silent one by one, the mission is no longer just about what new data it can send back. It becomes about everything it has already given us. Voyager's most important legacy isn't only measured in numbers, charts, or scientific breakthroughs, but in what those discoveries changed, how we see the edge of our solar system, how we understand our place in the galaxy, and how far human curiosity can reach. Today, they're the farthest human-made objects from Earth, silently cruising through interstellar space, and carrying with them one of the most profound and poetic ideas ever sent beyond our planet: the Golden Record. So the Golden Record itself doesn't target any particular star, but the chances of it ever being intercepted by an intelligent civilization are quite high, and that's why scientists wanted other worlds to reach our own world by sending what seemed to be a kind of cosmic greeting card. On each probe sits a 12-inch gold-plated copper disc packed with sounds and images designed to portray the diversity of life and culture on Earth. There are greetings in 55 human languages, music from around the world ranging from classical pieces by Beethoven to songs from indigenous cultures, and recordings of natural sounds like whales singing, wind blowing, and waves crashing. There are also 116 images, diagrams showing how to interpret what's on the record, and a printed message from then U.S. President Jimmy Carter. That collection is as much a message to ourselves as it is to any potential extraterrestrial listener. It captures who we were at that moment in history: curious, creative, complicated, and hopeful. It says that we, this small species on a tiny blue planet, had the courage to look outward, to explore, and to think about our place in the cosmos. Whether or not another species ever encounters the Voyagers, the act of sending those discs into the void stands as a testament to human curiosity and imagination. There's actually a philosophical richness to that act. The Golden Record is like a message in a bottle cast into an unfathomably vast cosmic ocean. Carl Sagan, who helped spearhead the record project, pointed out that if an advanced civilization ever finds it and plays it, that would be an extraordinary event. But even sending it says something deeply hopeful about life on Earth and our desire to connect across unimaginable distances. So when we talk about the broader implications of Voyager, it's not just about data and probes. It's about humanity's urge to explore, to communicate, to leave a mark, and to ask big questions about who we are and where we fit in the cosmos. If this journey of Voyager has inspired you even a little, take a moment to like and subscribe, because the universe is waiting, and who knows what we might find next. Thanks for watching. See you in the next one.